Welcome back to Advent of Code 2016. We're on to day 22. Let's begin. Grid computing. What's this going to be? Well, it's a short description. Looks like a graph. I like graphs. I'm good with graphs. All right. Grid computing. Gain access to a massive storage cluster arranged in a grid. Each storage node is only connected to the 4 nodes directly adjacent to it. You can directly access data only on node dev grid node XO. Okay, so 0, 0 basically. But you can perform some limited actions on the other nodes. Alright, you can get the disk usage of all nodes via df. The result of doing this is in your puzzle input. So, okay, fine. Oh my goodness. Interesting. Okay. You can instruct a node to move, not copy, all of its data to an adjacent node. Alright, and the numbers correspond to coordinates, makes sense. Before you begin, you need to understand the arrangement of data on these nodes. Even though you can only move data between directly connected nodes, you're going to need to rearrange a lot of the data to get access to the data you need. Therefore, you need to work out how you might be able to shift data around. To do this, you'd like to count the number of viable pairs of nodes. A viable pair is any 2 nodes, regardless of whether they are directly connected, such that node A is not empty, nodes A and B are not the same node, okay? The data on node A would fit on node B. Regardless of whether they were directly connected. So we're looking for all pairs? I mean, okay, so I don't think we want to brute force this because that's too many pairs, surely. It goes up to... Oh, that's not too bad, actually. 300. It'll be in the millions. That's fine, we can do that. Alright, we can brute force it. Alright. So let's copy in the input. You know what? I think ChatGPT is going to struggle with this because the input has some weird stuff at the start. Hang on, let me paste this in. So the problem description doesn't actually specify, you know, these 2 lines, but I suppose we can paste a sample of this to show ChatGPT what it looks like. That'd be good enough. Right. Okay. So I think the first thing we want to do is just build up a hash map which maps a... I don't think we need to use the the used percent column, because that's a result of. We just need to know the size and the used, right? That's all we need. And the percentage is probably rounded as well, so we don't want to rely on it. I mean, it's probably rounded, so. Well, then again, I don't think it is rounded. It looks like these are all nice numbers, actually. So it looks like it's actually exact. Either way, we just need size and used. Right. So let's copy some of this. So we've got we want a let's call it nodes. So for each line, if line dot starts with let's say this. Then we want to tokenize it. And then take the okay, so tokens equals line dot split. All right, now we need to get the X and Y values out. So tokens2 equals tokens dot split on the hyphen. The forward slash even. Oh. No, yeah, hyphen. X, Y equals int, so it'll be tokens to the 0, 1, but we need to ignore the X, so it'll be 1 onwards. And this one will be this up to 2. And so so now we just need okay, and we can grab this use size and used as well. Size equals int tokens 0, 1. And up to, but not including the last character. And used, or yeah, used equals 2. It's always T, right? Terabytes. Yeah. Okay. All right, that's all the information we need. And then put that into the nodes. Y equals size used. All right, so that runs. Okay. Now we just do a count for k nodes.items. So just do a double for loop ranging over the all nodes. If k1 is not equal to k2, so two different nodes, we want to say, so what was the condition again? Node A is not empty, its used is not 0. Okay, so if V1, so the used will be the second bit. It's not equal to 0, and then the other condition is the data on node A would fit on node B. Alright, and V1, so that's the data on A, and less than or equal to so it'll be V2 0, that gives the total size, minus V2 the used size. So that's the available size of V2. Alright. Let me zoom in here. Keep forgetting to do that. Alt Shift. Alright, and then at the total 888. I thought it would be in the millions. Wait, so it's like how many nodes do we have? Y goes up to 24 and X goes up to 36. So it'll be 24 times 36, and then but a lot of them have a lot of space used up. It's generally 70-80% used, so only a few actually have space. So yeah, maybe that's right. Okay, try it. 888. Correct. Part 2. Oh my god. This is complicated. Okay. It looks like it's going to be a kind of graph search. Like, okay. Now you have a better understanding of the grid. It's time to get to work. The goal is to gain access to the data which begins in the node with y equals 0 and the highest x, okay, top right corner. For example, suppose you have the following grid. So we've got y equals 0, x equals 2. That's the top right. So 0, but we can only access 0, 0. We want to access 2, 0. So we need to move the data from let me get this straight. What does it mean to gain access? You can directly access data only on 0, 0. You can perform actions on other nodes. You can see the disk usage and you can move data. All right. Oh, I see. We want the data from we actually want to physically move that data to... Okay, fine, that makes sense. Oh man, okay. The node you can access directly is almost full. The node... Okay, so we want the data on x2, y0, okay. Enough to fit on my node. Is that definitely going to be the case? Okay. Oh, we've only got 2 available. Oh, I get it. Okay, we need to clear space in order to move it in. Oh my god. Okay. Fortunately, 1-1 looks like it has enough free space to enable you to move some of this data around. So initially, the grid's capacities and connections look like this. Fine. Is this gonna be a flow problem? Not quite, but it's similar. Okay, so... Goal is to move the data in the top right to the node in parentheses. Yeah, we've established that. I think they're repeating themselves. Hello, Amaro. To do this, we can issue some commands to the grid and rearrange the data. So move the data from 0-1 to 1-1, leaving 0-1 empty. Yeah, okay. Move the goal data from 0-2 to 0-1. Move the data from y1. So now we move from 1. Hello, DJ. This looks like quite a complicated problem. Basically, we have a bunch of computers in a grid, 2D grid, and they all have like a size and how much memory is actually used up. And we're trying to move data from computer to computer until we get the data from the top right computer onto the top left computer. But you can only move all data in one go. You can't just copy some of the data. So you have to move all the data from one computer to another in one move, and it's got to be adjacent. So tricky. I mean, we can just do it as another search, good old breadth first search, which I've used a billion times now in this month. State space is very complicated though, because a state is an entire grid of capacities and usages, which is not okay. That's not that big. but it's just kind of take a while to code because we have to make a hash method and so. Alright, if we assume a state is basically like this snapshot here, but also a flag to indicate where the data from the top right computer is, then oh man, this is... Well, yeah, I could start doing that, but it looks like we'll need some smart speed ups here. I can do it A star, so basically the closer the goal data is to the start, the better. That's the heuristic for A star, just the raw distance from the goal to the goal data to 0, 0. That's a pretty good heuristic. It's just still, you have to move things around quite a lot to okay. Okay, let's just start coding something. This is I'll go with what I said, just like breadth first search across these states. The tricky thing is how do I find the neighbors? I guess every... Oh man. Every possible move command is... leads to one neighbor. I can't keep searching this grid for how many things can be moved around. That's expensive. So we need to do it once at the start. Keep track of all the possible movements. Oh man. Okay, fine. So we need... So we've got a set of nodes. We've calculated a total. That total is useless for part 2. I don't see any use for it. Oh, this is horrible. Okay, we have to start by creating some sort of class, and then we have to give it all the methods and hash method and equality and all this stuff. So, let's say class state. Alright, so a state has two things. A grid of all these things, nodes. So self dot. Okay, so we have to supply a grid. And goal location. Goal where yeah, call it goal data. The coordinates of where the goal data is. Okay. That's all we need, right? Now, the thing about the grid is we need to make it immutable. Right now it's a hash map. That's not, it's no good. So we need to create rows for Alright, let's have a look here. What is the width and the length? So y goes up to 24. So it's width 20, height 25, width 37. Okay, so n m equals 25, 37. Okay, so given Alright, let's change from this hash map to use a two-dimensional grid because that will help. So it'll be none for j in range, m for I in range, n. And then when we access nodes, so we use nodes y, x. Now and then we do for I in range. So yeah, for in range n, for j in range m. So it's I1, j1, and then for I2 in range n for j2. So we do if at least one of these pairs is different. 2 or j1, or just say this: if I1 j1 is not the same coordinates as I2 j2, then we do we say v1 equals nodes, let's just access, so be j1 I1 j1 v2 equals, this is just changing the hash map to use a two-dimensional grid array, so it's a bit messy. And now the rest should hold. So if I run this again, I get the same answer. Good, good. All right, we've switched to using a two-dimensional array. Now, given a two-dimensional array, we want to make it immutable. So we want to say self.grid equals tuple row for row in grid. So convert each row to a tuple and then put all those tuples in one outer tuple. That's immutable now, so we can hash it. Self.goal data equals goal data. Is that fine? Okay. Define equality. So it's a tuple of tuples of tuples, and the innermost tuples are just a pair of integers representing the size of the computer and how much is used. Why does it not like X? It's fine. All right, so okay, equality. This one, okay, it's easy. The way I've done it now, it's easy to do these methods. Return self.grid equals other.grid, and self.goal data is equal to other.goal data. Define hash. These are more confusing than 2015. I think the subject matter is actually more confusing. I agree. I think the problems are easier overall. but it is expressed. There's a lot of cryptography, and it's expressed. I think it's expressed in a way that people who haven't done cryptography or just mathematics in general would struggle more with unpacking the descriptions. But yeah, I think the problems are easier overall. Everything has pretty much been breadth first search or some variant of it. The hardest bit is always unpacking the description. But in 2015, there were some problems where I got stuck for hours, I think. So I do think this year is easier. So if I want to hash state, I have to return hash of self.grid and self.goal data. Okay, that is the basic state. Just make sure that compiles. Okay. So start equals state given the grid and the goal data. So the goal data will be the rightmost. So it'll be y equals 0. Alright, I've got to stop using x's and y's and start using i's and j's. So it will be row 0, column 36. Alright, this compiles. Change that variable there. Alright, this compiles, that's promising. Okay, good. Now, let's try printing start.grid. Let's see what it looks like. There we go. So that is the grid, but as a set of tuples instead of lists. So it's like 9268, which corresponds to first, the top left. And 8865 would be the next one across. So not this one, but we go down to x equals 1. 8865. Yeah, that looks right. And the beauty of this is that it's immutable, so it can now be hashed and stuff. Right. So, what next? We have to get all possible neighbors for a state. Now, there could be many of them, but we did print all the possible. So we printed 888, which is the number of moves that can be made in this graph. But that's actually an overestimate because it's the number of nodes that are not next to each other, not necessarily next to each other, that can move their data. But they do actually have to be next to each other, so the true number will actually be smaller than that. Which is good. That means the branching factor is quite low. So, and still. All right, so. We just have to make a overrides. Yeah, that's fine. Okay, so define get neighbors. This is always the hardest bit. the neighbor method. So right, so we have to start by checking. Okay, so a neighbor a neighbor state means we've picked a node and we've moved all its data to one of its adjacent neighbors. Okay, so we have to range over every possible node. So for I in range n, for j in range n. So we're now sitting on a computer, and the size and used values. Actually, we don't care about the size of. If we have a computer and we're trying to get rid of its data, we don't care about the size. We only care about how much used data is there. So we want used equals self dot. So it's grid I j 1. That's the used. Now, if it's empty, if used is 0, then we skip this computer because there's no movement there. Right, so we're now sitting on a computer, it's got data, and we're trying to see, can we offload this to one of the neighboring computers? So now we have to look up, down, left, and right to see if one of those computers can take this data. Okay, so for delta n, so it'd be 1. So this is just all the possible directions, vectors. -1, 0, 0, 1, 0, -1. Let's say for di dj, new I new j equals I plus di j plus dj. So that is a neighbor. If that might be out of the grid, so now we have to check that it's actually in the grid. If 0 is less than or equal to new I is less than n, and 0 is less than or equal to new j is strictly less than m. Alright, so this is a valid neighboring computer. Now we have to check how much available space is on this neighboring computer. So avail equals so we take new I, new j, so it'll be the size minus used. Okay, so it'll be 0, let's say neighbor size, neighbor used. used equals that. All right. Avail. All right. So if used is less than or equal to the available space, which is the neighbor size minus the neighbor used, that means we can actually move this data to that computer. So what happens? So the used space from the current node will go to 0 because we're copying all the data across. Not copying, moving all the data across. Okay. So we need to make a new grid. So new neighbor grid equals list equals list row. This is basically turning all the tuples back into lists for row in self dot grid neighbor. So now we need to change neighbor grid. Let's say size used equals that. So neighbor grid ij is size, same size as before, but now used drops to 0. So we're modifying this neighbor grid to look like the new state. So we've deleted all the data from ij, and we've added all that data to neighbor I, neighbor j, new I, new j. So new I, new j equals, so the size will be as before. That never changes. It never changes, so this we shouldn't even be storing the sizes in this data structure. That'll save space. The only thing we should be storing in the data structure is the used quantity. Okay, let's do that because that will actually save space and time, I guess. So, yeah, the total size of a computer never changes throughout this process. The only thing that changes is the used data. Okay, so let's create a constant called size equals that. So let's say used is this, size is this. So size we change to just be size I want to start using i's and j's, not x's and y's. So we say ij equals yx, just so I don't mix things up. So now size ij equals that, and used ij equals that. So far so good. Used size will never be touched again now. So now in this one we need to say so used 1 equals used that. Used 2 equals used. So then we got used 1. So that's saying that's just an integer. So used 1 is not 0, and used one is less than or equal to size minus used 2. All right, we should get 888 again. Damn it. Used. Used is accessed differently. Used I J. Eight, 8. Okay, fine. What we did is secure. All right. Okay, so now what's wrong here? Nodes. There's no nodes. All right. Used. And we need to change. So used. Don't call it grid, call it used. So that makes it clearer. So now used is no longer a it just has integers instead of pairs of integers. That's simpler. All right. So here we use extract used. So we don't get size, but neighbor used is that. So if used is less than or equal to size, minus maybe used. Okay. So call this one new neighbor used. So that'd be a list version of the tuple, and now modify ij to be 0 and modify the uj to be neighbor used plus all the data that we copied across. And then finally, new state equal, the goal. So if new goal data equals if the goal was in ij, then it moves across, otherwise it stays what it was before. So it's going to be ui uj if self.goal data is ij, else it will just be whatever it was, self.goal data, doesn't change. So we move the goal data, critical data over, possibly, and then now we yield the state that's created. Oh my god, this is horrible. State given the new neighbor used and the new goal data. I think that's correct, but we have yet to test it. So that is how we get neighbors. Now we do what we've done a million times before. We write BFS and maybe upgrade to A star at some point, because I think it'll take a long time. There's a lot of branching here, so let's see. Print length of start.getNeighbors. How many neighbor states are there? Okay, fine. Listify it. You can't do length like that. It's supposed to make sense. All right. Used is less or equal to. So we've got DJ being -1. Okay, fine. This should be UI. This should be UJ. Try again. So now it's 4. Just 4 neighbors. That took a long time to compute, though. Oh no, that was computing 888. Hang on. Let's just disable part 1. Okay, it's quick, So there's only 4 neighbors, so actually there's not much branching. Maybe we have hope. Okay, so don't need that. Now define BFS given a start. So we want to find the number of steps it takes to get to any state in which the goal is residing in 0, 0, basically. So we want to import Q, import Q. So we want Q equals Q, Q dot put start, dist equals that, dist start 0, that's the setup, while not q dot empty current equals q dot get. Now we do the goal check. Or we can do the goal check when we find the neighbors, to be honest. Save a bit of time. Alright, so we don't do the goal check. Yeah, okay. So we've got the current. The BFS is actually going to be really simple because the neighbors was the complicated bit. So current equals q dot get. Okay, so it's just for neighbor in current dot get neighbors. It's unlikely we'll revisit states, but we should account for that possibility. It's valid. It's a valid state. You can move in infinite cycles, but we don't want to because that means we're just wasting time. So we'll skip all the places we visited before. So if neighbor in dist, skip it. Dist of neighbor equals dist of current plus 1. And we're going to put it in the queue. But before we do that, if neighbor dot goal data is 0, 0, we return the dist value. That's it. That's the goal. And then we put neighbor into the queue. Q dot put neighbor. And then finally, we just want to print BFS of start. Alright, I've typed a lot of stuff without actually testing anything intermediately, so now we just run it. Grid. I'm still trying to access grid. Wait a minute. Ah. Alright, now it's running, and we'll see if it actually terminates or not. Okay, but then we have to start thinking about speeding it up. I don't see many clever ways of speeding it up. It seems like, okay, we can use A star, certainly. That's actually gonna help. Because currently it's probably just moving the goal around randomly. It doesn't have any notion of progress. It just keeps moving the goal back and forth. We could leave it running for a bit, but it looks like... Well, we can start coding A star while we're waiting, so... mean, there's a lot of... Yeah, we've got to do A star at the very least, and probably even that might not be enough, I'm not sure. Oh, well, at least we can try it on the examples, so... then it'll tell us if it's actually coded correctly, so... Okay, we can put that back. Right. So... simpler case. Zero 3. Why is it trying to do 0 3? Ah, because nm. Okay, fine. Nm equals. So in this example, it's 3 3 3. None? Okay, doesn't work at the moment. No gold found. Okay, fine. Okay, so are we? Oh man, there's so many things that could be going wrong. Goal data, is goal data definitely being copied across? That's the most important thing, because that's the termination condition. So that's where we change goal data. So new goal data equals new I new j if the goal data was an ij. Yeah, that's right. Otherwise, it's whatever it was before. That sounds fine. We've got to start printing stuff then. Alright, so we do have a disk table. How much stuff does it have? Okay. Print, let's say state dot goal data for state in this dot keys. See where the goal data arrived at in all these cases. Print. $0.36. We never moved the goal data. Never moved the goal data. Hang on, 36. Oh, I've hard-coded numbers here, haven't I? Damn it. NM 33. So what? How did we get to 30? Ah. Okay. So it should be 0 row 0 column m minus 1. 7. Correct. Now run it again, but it's probably still going to take too long. Oh, no, if it's actually making progress now, it might actually work. It's taking too long. Okay, fine. Next step is to let's print some other stuff. Print neighbor.goal data. We'll see what's going on here. $0.36. Why it's never changing? Oh my god, okay, so why is it never changing? Are there too many branches that it's never choosing one where it changes? It should. No, because we ran it on the simple example, so okay, I think we've got to switch to A star then. Even so, I'm not too confident with A star. Alright, so A star. So it's going to be a priority queue. Alright, I think ChatGPT will fail this one. This one's pretty complex. Alright, so queue equals priority queue, queued.put start. So we need to define h of a state, return state.goal data zero plus, it's just the Manhattan distance that where the goal data is from 0, 0. Alright, so queued up with start. So you put a tuple, put h, start. Let's make it explicit. 0 plus h. 0 is the accumulated distance, and h is the predicted distance. Start it there. Alright, dist. Okay, so now, while not queued or current, okay, so we don't care about the h. So, it's queue.get. Now we have to do the goal check here. We can't do it later on, so we've got to do this here. If current.goal data equals 0, 0, return dist current. Okay, that's the goal check. Now, for the neighbors. For neighbor in current look at neighbors. If neighbor okay, so if the neighbor's already in the dist and dist, the previously known distance to this neighbor is actually better than what we're looking at now, then skip this one. We've found a better path somewhere else, okay? Otherwise, we say dist neighbor equals that. Q dot put, so we have to do dist neighbor plus h neighbor, the predicted distance, and then the neighbor okay. Try running that. Not less than, not supported. Always gotta do this, okay. Either you make a wrapper or you do the more hacky way, which is to override okay. Now we're using the heuristic. Still taking a long time. Okay, I'll just interrupt it. I want to see if we're actually going anywhere. 36. So it's just moving stuff around. But never moving the goal. Alright, let's go back to the example data. Make sure this still works. 7. Alright, so yeah, it is moving the goal around. So now we just... what do we do now? So far, this seems correct. It's just taking forever. Can we find a better heuristic? Not really. The Manhattan distance is pretty much the best heuristic. I can't... I have an idea. let's sort of all the neighbors pick. Oh no. We should really, the moves we're making should really be, we should really start with the ones that are closest to the goal already, because we're trying to move it around. But do we ever move the goal data if swap 0 swap? That's correct. Let's try n-2. I'm just curious if we actually. Okay, it's always at 35. Try moving it closer. Just move it to 1. I wonder if we're stuck in a loop. Let's make sure we're checking for. If let's change that to less than or equal to, because if it's equal, we can skip that. What else? I think if I'm not using a closed set. You should always have a closed set. How many times have I written A star and I always forget this? Dist is, I was using dist as the closed set, but that's wrong. Dist is not the closed set. Closed set is separate. So it's probably stuck in a loop. Only when we pop on the queue, that is the best distance for that. So we say if current is already in closed set, that means we've already found an this is duplicate. That can happen. So continue closed set dot add current. Right, now this has to be used, closed set. So for neighbor, if neighbor in closed set, skip this one. So this should not go into infinite loops now. No. current enclosed set already, skip it. Otherwise add it. So that means this node is exhausted. We never need to visit this node again. We never need to pop anything with this node. But that's just one state of many. Oh god. Stop this. We should be getting new goal states. So it still could be stuck in an infinite loop. So we've got closed set, we've got all the things you need, right? Dist start 0, closed set, okay. So we skip neighbors for which we found a better path before. Am I putting the correct values in? So the only puts we do are here, where we put the H value of the start. And here we put distance to the neighbor plus the H value of the neighbor. Something's not right here. Okay, try H value 0. So this goes back to BFS basically, like extra or whatever. So still not moving the goal. There's just so many possibilities for these used values. That's the problem. So it's probably just doing lots of different moves. Oh. Node 0. So the data is on 0 m minus 1, so it's going to be row y equals 0. So this one here. So the data is 67 terabytes. We need to get this 67 terabytes into why have they given us the use percent? Is that of any use as a heuristic? We've got a bunch of big we've got a bunch of nodes that are full, and there's no way you'd ever be able to get data off them. But I mean, we're already accounting for that. That's not slowing us down. We're not trying to move data out of them. It's interesting that they exist. So all these ones with 98% are kind of shouldn't touch them. They're just blocks. We're supposed to do something with that. We need to find some sort of clever speed ups here. So I'm thinking does this work the other way around? No. If we... let's print. We need to print some more data here to see what's actually happening in this. So print dist. I've not checked the dist value. Let's have a look. Print dist neighbor. Should be increasing. 5, 6, 7, 8. So we move to 8 levels of depth. 9. Oh man. 10. We need to find a way of cutting out all this redundant stuff. The problem is there's lots of moves we do that are not even relevant. And we keep doing them all the time. 11. Alright, try something else. If neighbor dot goal data is not equal to 0 and -1, print neighbor dot goal data. Try that. Do we ever move the goal? So the goal data is in y equals 0, x equals 36. It's 67 terabytes. Need to move that somewhere. Why did they have us do part 1 where we... where we calculated all possible pairs of computers that could swap data, because it's why would that help us? There's 888 pairs of computers that can move their data from one to the other. Why did we compute that? Because they're not adjacent. If we knew that the data can go somewhere. Hang on. Let's have a look at these blockers. Maybe this is a trick. Alright, let's have a look. 36, y equals 3, x equals 36. Y equals 3, x equals 35. Y equals 3, x equals 34. Oh my god, there's a barrier. Y equals 3, 33. Y equals 3. So basically, we never do anything with y 3 or greater. Is that the trick? This is why sometimes you should just print the data visually and see what you're actually dealing with. There's actually an actual barrier at y equals 3. So I'm messing around with everything from 4 to 25, but it's all useless. Oh my god, okay, fine. Wait, let's make sure that still holds. So, yeah, y equals 3, 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 equals 3 equals 3 3. Wait. I can use programming to do this, but I'm just too lazy at this point. Equals 3. ChatGPT is not going to be able to solve this because it's not going to be able to look at this data and work this out. This is something you have to actually be human for now. Yeah, it looks like it's holding. I'll just assume it holds. Let's go all the way to the top. Oh, that was a clever problem, actually. Well, actually, so here, x equals 0 is actually usable. Well, when's the first time we get something big? Y equals 3, x equals 1. So basically, if y is... What does this mean? So, but we do... So x equals 0. So it means we have a barrier from x equals 1. So at the third row, we have a barrier from 1 upwards. But there's actually a gap at the left. So you can move data down into the lower half. Okay, but oh man. So I was hoping it would be fully blocked off. It's not. All right, let's try it as if it were blocked off. See what happens. So basically, yeah, we don't want to do that. So basically, we want the neighbors if I is greater or equal to 3, skip that one. Don't count it as a neighbor. This is probably wrong though, but if I... Let's see what happens. No goal found. Damn it, so you do actually need to... Oh. You do need to channel data through that gap. Alright, so we've found out something, but what? I don't know what we can do with that information. So there's a barrier across y equals 3 row. So that means there's 0, 1, 2. There's 3 rows above, which we can move stuff about. And there's a barrier. There's a tiny little gap on the left where x equals 0, where we can move stuff. And then we're back to normal nodes. What the heck do I do with that information? This is horrible. So we can't move stuff through at y equals 3, but we weren't trying to anyway because it's full. It can't actually take any data. So we have to be moving data from the top half to the bottom, it seems. think instead of single moves, we have to start thinking about chains of moves. Because think about it, if we're gonna move goal somewhere, then we're moving it to a place where we had to move that data somewhere. And that data had to be moved somewhere. So basically we have to pick a spot somewhere in the graph. And in one chain, move all the data up to that. How do I... Okay, I think this is getting somewhere, but it's going to minute. I think I'm now seeing why they wanted us to calculate that 888 different pairs. So, okay, how long have I spent on this so far? Just up to 2 hours. This might be the first time I actually need to carry on with this another stream. Yeah. This is gonna take a bit of work. Well, let's keep this train of thought going for now. So So I think we got to think in terms of chains, because you don't want to... Like, what the problem is, what I'm doing is I'm moving stuff on this computer here, and then the next neighbor is I'm moving stuff from this computer to here, and this computer to here. It's all disjoint, and there's no point to it. What we should be doing is grouping them together, so you only ever pick a chain of computers, a continuous chain, and then in one simultaneous move, you move all the data from those computers forward by one in that chain. Because you have to, otherwise there was no point in... Because the whole point of that chain is it then frees up a space next to goal, and that goal can move somewhere. So we have to look at those chains. So that's one thing. And also, look at these numbers. These are all very small availabilities. Who actually has space for any of this data? It's always too small. Like, nothing can be moved. So I think the problem statement was giving us hints that we don't need an algorithm which is like works on any case. We need to start tailoring it to this kind of degenerate data that's kind of it's non-random. It's very much designed. Yeah, I can't find any computer that has any space, but I think there were like 4. So this is... How are there 888 possibilities if... Interesting. Let's have a look at starting state and print all the possible... Right, don't do the A star now. Stop that. So print this again. And list start get neighbors. Huh? Oh, because I'm doing this. Okay, take this out again. So it should be 4. 4, okay. Print the list. Okay, fine. If we're yielding, then just print I, J, new I. I want to see what the moves actually are. Because I'm not calling it. Alright, these are the possible moves. 619 is the only computer can take on data right now. So it's like, alright, let's have a look at these. 619. That's y equals 6, x equals 19. X equals 19, y equals 6. So this is the only computer that has free data. So it all revolves around moving stuff to. So the first move has to be something goes to 619. Okay, but A star was already accounting for that. Fine. So actually, this is less about branching states, and instead we should find a path from 619 to our goal data, which is continuous and allows the data to be moved. But there could be many such paths, but how much space does it have? Has 93 terabytes, so it can take basically anything except for those gigantic ones. Not necessarily. Oh no, it can, because they used. So it can take anything basically. I think they're just trying to trick us. Basically, all of these guys can actually take any of these guys. So actually, it would be better if we just replace these numbers with like all of these with 100s and all of these with like 50s or something. No, not 50s, like 75. So it's just 60, so you can't fit 2 in 1. Then there'll be less branching. let's try that then. So let's change these numbers. So now just change the size to 100. So if it's less than 100, just change it to 100. And then change this to 75, let's say. No, don't do that. Say... Yeah, if it's less than 50, set it to 0. If it's more than 50, set it to 100. So it's either full or empty. Completely full or completely empty. Then we're dealing with discrete numbers. I think this is the better way to do this. Right, so... size equals... let's say 100 if whatever the true size is less than 100, else, I don't know, 500 or something. Okay, and we used so we say if this is less than 50, then the used is 0. Elif that is less than 100, then we say the used is 100, else we say 500. So everything is 0, 100, or 500. So the 500 ones are full up. Everything else has 100 size and is full. This was what they wanted us to do, I think, and that's why they gave us such a complicated description. I should have paid more attention to that. So basically, all these changed to 100s, with the exception of the one which has 0. Oh, okay, let's try that now. Now we don't have as much branching. It still might take a long time, but this is getting somewhere now. So. Print. Okay, run. Now the goal is moving about. Oh my god. Oh my god. But this printing is helping us. Alright, let's just run it then. That's actually cut down the branching factor. What's all this printing? Why am I printing stuff? Stop printing stuff. Ah, bollocks. Every single one of these is doing this. Okay, fine. Alright, let's see if the goal actually changes now. Now it's a sliding block puzzle, isn't it? It's not a it's not a breadth first search. Well, it could still be, but we need we just need a path that goes from... Oh my god. Is it that simple? Is it just that we need... Oh my god, I think we can solve it by hand. Hang on. So, what was it? It was y equals... No, it was x equals... Where is the 0? It was... X equals... Where was it? It was x equals 19, y equals 6. So from 0, 0, you can move stuff down 6 spaces, and that avoids the big barrier. And then move stuff across 19. So that's 25 moves. But the other way around. So we're moving the blocks into 19.6 one by one up until we get back to 0, 0. So that's 25 steps, right? And that means 0, 0 is free up. Now, no, what am I trying to do here? No, that's not quite it. Okay. I need to draw something, don't I? We have... So we have the top left. So, God, I need to... Yeah, okay, so we've got the top row. Then we've got the goal over here. And we've got another row, like this. And we've got another row, 0, 1, 2. And then we've got another row, but this one has X's, meaning that's impenetrable. And then we have a normal row. And then at 19, 6, y equals 6, so 0, 1, 2, 3, 4, 5, 6, x equals 19, so somewhere we've got a gap. That is what our map looks like, right? So let's make that space. Right. Okay, so this can be solved by hand, I think. So we just have to... What is the minimum path that will take G to the top left? So I think first we move all these things down and into the gap until we have a gap here, like this. So how many steps does that take? So this is 0, this is 1, this is 2, and then this one is 6. So it will be 19 moves to move the gap all the way to the left. And then another 4 to move it there. Yeah, 6, 5, 4, 3, 2. So now we've got the gap there. Actually, move it right into the top left. So 2 more moves, and it's now there. So that's 6. Now we have to do a rotation to get G into that space there. What is the fastest way we can get G over there? Well, we can do a full rotation of these 2 rows. So that will move all these guys like, what's x 0 to 36? So if we move all these guys to the left, that costs us 36 moves. Move. Oh, interesting. So now, if we want to move G to the left by 1, we have to move this one up, this one to the right, this one to the right, and this one down. So that's 1, 2, 3, 4. If we do that, so that costs us 4 moves. And then G ends up here. And then we just keep doing 4s, don't we? Until G ends up in the initial position. Is this actually going to work? So right now, G is in 35. No, where is it? It's 30. I can't process this. I've lost track of where I was. It was 19 moves to get the gap to the left, 6 moves to get it to the top left, and now we just have to move G. So it was like 19 and 6 got us to here, right? And then 36 moves brought G to x equals 35. Now, it costs 4 moves to decrease G's x value by 1. So basically do 4 times 35. So every group of 4, it's an up, right, right, down, and a left. So actually 5. And then G ends up to the left by 1. So at some point G will end up like here, and there'll be a gap to the right. And again, you would do 1, 2, 3, 4, 5. Okay, so I think the answer is that sum there. I've just solved this by hand, maybe, but I don't know if this is even right. Print 19 plus 6 plus. Even if this is wrong, I think I'm along the right lines now. I would just have to get it, just do that argument again, but make it rigorous. 236? Oh my god, if this is the answer. I could be like 1 off or something though. Oh my god. No way. There's no way ChatGPT is solving this. No way. He won't be able to. Unless I gave him the input, but we can't really give him the input. So unless he writes an algorithm which smartly works, that was a brilliant problem. Now that I see the trick, I think the trap people fall into, which is what I fell into, is trying to write an algorithm which will handle any input. It's hopeless because there's just too many possibilities of moving things around. You just have to look at the data, maybe draw a graph of it, or like a heat map or something would have helped me so that I could see which ones are more full, and realize that you've got a barrier, and then it becomes a sliding puzzle because you can't actually move two computers to one empty computer. It's always just moving everything from one to another space to another. So it's just a sliding puzzle. You just have to discretize it. Well, it's already discrete, but you have to discretize it even more. Oh my god, that was a good puzzle. How long did that take me? Just over 2 hours. How long did it take people? Let's see. Probably much faster. They would 22. Leaderboard. Really? It's 14 minutes. Okay, fine. They've probably seen 1 hour 30. Okay, so I wasn't far off actually. God, okay. I mean, I could almost just call this a loss for ChatGPT, but we have to give him the chance, so. Alright. I'm pretty sure he'll manage part 1. Well, we have to show him what part of the data looks like. Okay, so how are we gonna... We're going to do this. Let's say that was a very, very smart puzzle. Actually, that was a lot of these problems in this month were very textbooky, but that one really makes you think and stop and look at the data, which is very important in like AI and machine learning. You got to actually look at the data and see what's unique about it. You can't always just write algorithms that solve every case, basically, because you can't. It's too many cases. Alright, so this is the problem. But I have to give him a sample of input. Alright, count viable pairs. He'll probably manage this. Yeah, that looks good. No way is he managing part 2 unless he's just copying something he wrote for someone else. Alright. 888, correct. Now, unless he really picks up on the clue that they were giving here, and admittedly I should have just done that because they're not going to write clues in the description without there being a reason for it. Like, look, they said they gave clues and I was just dismissing them. Most of the nodes are interchangeable. They're full enough that no other node data would fit, but small enough that their data could be moved around. That was the clue. That it's a sliding puzzle and not an exhaustive search. Okay. A very large full node as well. They mentioned that as well. So if ChatGPT picks up on that clue, and he pays better attention to the words of these things, because I just skim over them, maybe he will actually solve part 2. Right. Now, adjust for the following modification. No. Right, part 2. A search algorithm such as breadth first search or Dijkstra's algorithm. Not gonna work, I think. So I'm not gonna keep trying. But I'll tell him once that it takes too long. It might work. Maybe I just really wrote breadth first search badly. It's possible. But I'm pretty sure you had to use the trick. Okay. This is probably like technically correct, but just not good enough for the data. Main input file. Can only concatenate string, not int. We have to wait for this. I'm satisfied with that now. I was feeling frustrated with that problem, but it was just I was too used to all the previous problems where it was always just write breadth first search and don't worry about what's actually in the data. Should work correctly without any errors. Don't make promises you can't keep. Oh. It's not accounting for the letter T. No, he's not cutting it off. keep at it, but it's not going to work, is it? I have to at least give him a chance to try, because if it works, then that's going to annoy me, but... I'm going to have to look up discussion on this, because it'll be a very interesting discussion. I can't believe I actually solved it by hand. I never actually needed to write any code for that. It could have been solved completely by hand. It's... all the numbers are like less than 50 and you just have to slide things along. There's a very strange part 1 though. It didn't end up being important. Result equals main input file. Okay, print result. He forgot to print it. 592. Nope. But why on earth does it actually terminate? This shouldn't be terminating. It should take too long. How? It's just a basic BFS. How is it actually terminating? It's wrong, but it's... Okay, what does his neighbor function look like? That's start node equals goal node. Yeah, okay. Well, neighbor and get neighbors. What does the get neighbors look like? Directions. For a given node in the grid. Specifically a given node. Huh? Current node. That's weird. Maybe he is going along the right lines here. Maybe he's treating it as a sliding puzzle then, and not what I was doing. His states appear to be the actual individual nodes, not the actual full grid. Oh, wow. He is using the hint. He's discretized it to just this, this, and this. No numbers. Okay, that's very smart. It's just got the wrong answer. But this is actually... I'll give him another chance, because that's actually... That actually looks good. Ah. Yeah, I see what the problem is. He doesn't know about the barriers on y equals 3. Okay. Maybe it would be fair for me to paste some of this input. No, I'll just give him this and see. One last chance. Goal node is not necessarily in the top right corner, but rather in node with y equals 0, and that's not the issue. Well, he's getting remarkably close to the correct solution. I just don't think he's using this barrier thing correctly, because he doesn't know, because he... Wow. Oh, it's not finished generating. Alright, it's still generating. Wait. Okay, there we go. Okay, this is the correct answer. Oh my god. 499, no. I think just call that a loss for ChatGPT, because I don't think he's gonna get anywhere if you can't analyze the input. But it's close. If I was able to give him the whole input, which you can't do with this website, it's too big. But if I had the paid version, maybe he'd be able to solve it by analyzing the input and maybe figuring out the pattern. But... Okay. That's a win for me. But it was a valiant effort by ChatGPT. Alright. Wow. Good problem. That's the kind of problem we need, like, throw us off balance. Stop us from making assumptions. See, look, 1262 did only this part 1, but didn't solve part 2. So there's a high proportion. Alright, we're almost there, just 3 more days. Alright, I've got to stop there. Never mind. Alright. Alright, that's probably the longest any of these problems has taken me so far. But that's not that bad, actually. 2 hours. That's not too bad. Certainly in other months I've had problems which took way longer than 2 hours. Alright. See you next time for day 23.